Hello and welcome to today's webinar presented by Dlubal Software. Today we'll be working in our finite element analysis and design software, RFEM. The topic for today's webinar is AISC 360 2016 Steel Member Design in RFEM. My name is Amy Heilig. I'll be your presenter. I'm the CEO of the U.S. office and also a technical support and sales engineer. We are located in Philadelphia, Pennsylvania. My colleague Wieland Gotzer will be your moderator, answering any questions you may have. He's a product and customer support engineer located in our Leipzig, Germany office. If the control panel does seem to get in your way when you logged into this GoToMeeting, feel free to show or hide that with the orange arrow up at the top. We always want to encourage everyone to ask questions throughout the webinar. You can do so within this same dialog box. We'll do our best to get to all the questions, but if by chance we don't, I'll certainly send you a follow-up email afterwards. So regarding the content for the next hour today, we want to go over a steel structure within RFEM. We'll model, load, and fully analyze that structure. Then we'll move on to design per the AISC 360, and in particular the new standard, the 2016 for ultimate and serviceability limit state design in our add-on module RF-STEEL AISC. We will review both the analysis and design result output in RFEM and our add-on module. And I want to go over significant changes that were made in the 2016 standard and how they were applied in our programs, including the add-on module RF-STEEL AISC. For those of you who are not familiar with our programs, I just quickly want to explain RFEM and the add-on module concept. So RFEM is our main program. This is where we will fully model the structure. We also integrate with BIM software such as Tekla, Revit, AutoCAD. We'll fully load the structure and we can run an analysis. In RFEM, you'll also get your analysis results such as internal forces, deflections, support reactions. Now, as far as design per the AISC, that requires our add-on module RF-STEEL AISC. This will provide us with the ultimate and serviceability limit state designs per the standard. We'll also be entering in some additional information that's relevant to the code only for design, such as unbraced lengths, limiting deflection ratios for serviceability design, as well as optimization of our cross sections. With that said, we can jump to the RFEM model. So when we go to create a new model, we must first give it a name, and we'll call this one AISC Webinar. And the type of model will be 3D. We can generate load combinations automatically. So within this drop-down box, you'll see here that we have the ASCE 7 2016 implemented into the program, as well as many other standards, including the Canadian standards. Now, if you prefer to create those load combinations manually, all you need to do is just to uncheck this box. We go ahead and click OK, and then up pops our new model. You'll see here that we have our graphical window where as we begin to model, we'll see our structure generated here. We have our tables to work with down at the bottom. You can import and export directly to Microsoft Excel at the click of a button. We have our tools to work with up here at the top, which we'll be utilizing today. And lastly, we have our project navigator over on the left, which I think is a little bit more unique to our program. Under the data tab is all of our input data. So as we begin to create this model, we'll see all of that input data available here. If we scroll down, we have our long list of add-on modules. The display tab, which we can see right next to it, is going to control everything that we're viewing graphically here. So for example, later on, again, I'll show you how to change how you're viewing your results, for example. Now, lastly, once we run an analysis, we will be able to see our results available in the Project Navigator. So to begin with, we want to start off with drawing a truss. Now, we could normally go in and create our members individually and snapping to different points, but under Tools, Generate Model Members, we have several structure generators here. 2D frames, 2D trusses, 3D frames and trusses. We can even generate stairs. So we'll start off with a 2D truss. And up pops our dialog box, and you'll notice that we have many different options when it comes to truss design. In addition, you can specify how the diagonals will be laid out or our web members. So if we take a look at some of these different options, they will go ahead and update depending on which selection we've checked here. So we'll start off with this second selection, and our diagonals will be the default for this first selection. The parameters is just our geometric information. The number of bays, we can set this as 6. The total length, which would be the span length, we'll set this as 50 feet. The total height is going to be measured right here at the center line. That can be set to 7 feet. Now we have a couple other options here. We can lower the lower chord member here by a certain distance. For example, if we set this to 10 feet, you'll notice how this picture changes. Same goes for elevation. If we make some changes here, then our picture is updated for how our truss will be generated. So moving on, the cross sections and member types. So we must define the cross sections for our chords, both upper and lower, as well as our diagonals and verticals or our web members. The program's telling us that we need to create a new cross section. So for this, we will open up our cross section library. You can see here that we have many different cross sections. For today, we'll begin with the rolled sections, and in particular the HSS. So when I enter into this dialog box, over on the left, we have some filters. So for today, we'll be working with the AISC, but you can see here the ADM, we have Canadian sections, and even further, we can filter to the AISC 14th edition or the newest 15th edition. Now, for square and rectangular HSS members, we do have a rather long list. So what's useful in this situation is to create a favorites group. With a favorites group, you can select a handful of sections that maybe you use quite often. And for today, I created a favorites group called USA that just has some sections relevant to today's webinar. So now for my rectangular HSS, I can choose my 12 by 8 by 0.5. Regarding material, when you first create a new file, concrete 4000 PSI and steel A992 are going to be the default materials. For an HSS section, we actually want to choose a different material from our database. For this, you can import in from the material library. Now, this looks similar to our cross sections. Over on the left, we have our filters, which we'll set to ASTM, and we have implemented the latest materials from the 2016 standard here. Again, an even longer list. So we can utilize that favorites group where we've added a handful of materials. And for our HSS, we'll utilize steel A1085. So this is a more recent material. It's been around for a few years, but more recently, the AISC now recognizes it within the 2016 spec as an approved HSS material. So we want to utilize that as well, and same goes for 1065. Here are material properties listed down in the table. So once I've created this material, I can choose it from my selection box here. We click OK. And we click OK once again. Now, that same material and cross section is populated for all of my members. Well, for the diagonals and verticals, I actually want to create a new cross section type, again under HSS, under my favorites group USA, and this time I want to choose a square HSS 5 by 5 by 0.375. I want to choose steel A1085 for my dropdown. You can see I accidentally entered it in twice here, no problem. We'll select the fourth material here, 1085. That will always be available now when I go to draw a new member because I've defined that material within this particular file. And I click OK. For the verticals, we've already defined the 5 by 5, so now I can choose it from my drop-down box here as well. Regarding the member type, this is important because you can see here that we have many different members within RFEM. You can choose a beam member, a rigid, tension only, compression only, cables because we are a nonlinear analysis program. So a beam member is going to be nothing special, just a typical beam or column. But a truss member, which you can see the program automatically inputs here, is going to set a moment end release. So we're only transferring axial and shear forces. So that's just a quick application rather than manually applying those moment releases for our web members here. So once we're done, we can click OK. And you'll notice that, as I said, our input material is listed here. The blue is what we're not using. So I input steel A1085 twice. All I need to do is to select that, hit the delete key, and now we only have one listing of 1085. Okay, so moving on to the columns, I'd like to just draw a member as we would within our toolbar, a new single member. I want to define a new cross-section type, and I'm going to choose my rolled hot sections, but a W shape here. And activating my favorites group down here with my checkbox, I've added in some W 10 by members. So maybe I'm not totally sure which 10 by member I want to go with yet, so I'm going to select one of these sections from my favorites group. We'll start off with a 10 by 88. Now, STEEL A992 is one of the defaults within the program. Now, currently, it's set to the 2010 standard. At some point when the 2016 is more widely used, we'll transition to the 2016 STEEL A992 to be default. But for now, if you'd like, you can utilize this just for consistency to change this to, instead of the 2010, to the 2016. So STEEL A992, we'll click OK. The member hinges, we'll leave these as fully fixed. We'll see a little bit later on how to apply a moment end release. I click OK. Now, typically, I could snap from one point to the other to create my columns, but we have a nice feature here where all I need to do is specify the length and direction. So I'm going to specify my columns at 20 feet in height, and I want to draw this column member perpendicular to my current work plane, which you can see here in the negative direction. So now when I just snap to the end nodes of my truss, I hit my right key to, or my right mouse key to escape, you can see that those columns were automatically drawn in the right magnitude and direction. Okay, so now that we have our first frame and truss drawn here, I'm going to use my selection box, and you'll notice that I'm paying careful attention to not select my nodes down at the bottom, and there's a reason for this. So just like in AutoCAD, with this selection box, we drag it over our frame, and I'm going to turn this into wireframe view and zoom in here. Holding down my control key, I'm going to unselect a couple of these nodes at either panel point on either side of the truss. Now you can't really tell graphically, but again, there's a reason why I'm doing that. So we're going to move on to the Move Copy tool. We're going to create 3 copies in the global Y direction of 20 feet. So Move Copy, nothing too special here. But under this option, Edit Expanded Settings, if we take a look at this, we can actually create lines between copied nodes. So this is why I was careful to highlight some nodes and not others. Now, even more so, we can assign a cross-section to those copied lines, or in other words, we're going to create members between the copied nodes. Now, if you want to utilize one of the cross-sections already within the model, you can select it here from a template member, or we can access our cross-section database. This looks familiar from what we've seen before, and we can choose once again a new HSS member. This one will be a 6 by 6 by 0.625. From my drop-down, I can select my STEEL A1085 material. I click OK. The member hinge, right now it's set to fully fixed, so that's what a beam type is. Now I could easily change this to a truss member if I'd like to release the moment by just simply changing the member type here, or you can always manually apply a member hinge. So by creating a new member hinge, you'll see here that we have 6 degrees of freedom, 3 degrees in translation, 3 in rotation. You can fully fix or fully release these. The program's making the assumption that you probably want to release the moment. We also have partial fixities with these spring constants. So if you don't have fully fixed, don't have fully released, but somewhere in between there, then you can specify this spring constant for any one of the degrees of freedom. Lastly, we do have nonlinearity. So if we take a look here at diagram, for example, and expand these details, we can account for things like tearing or yielding for our member ends. So quite powerful in terms of the nonlinear capabilities as well. For today, I just want to create, let's see, a moment release. So if I hit OK, that moment release will now be available. That's member hinge number 1, and I can select it from my dropdown for the member end as well. So I click OK through all of these dialog boxes. And you'll notice now that our structure was generated at the click of a button. So turning this into rendered view, these were the members that were created between my copy nodes. So again, this is why I paid careful attention to select some nodes and not others. At the bottom chord, I don't have any lateral restraints here except at the midpoint, which you can see I left one HSS member bracing my bottom chord. So that's really it as far as the geometry for our structure. Now we want to support it. So up in our tools, we have a new nodal support. We also have a line support for maybe the bottom of a wall. And next to that, we have a surface support for, let's say, a slab on grade if we want to apply soil spring stiffness. For today, we're sticking with the new nodal support. We have some defaults here: hinged, rigid, fully fixed. We also have sliding. Of course, you can create your new nodal support definition, and this should look quite familiar. This looks like our member end conditions. We have our 6 degrees of freedom. We have partial fixity here, and we have nonlinearity to take into consideration if we'd like. Now, nonlinearity might be important for sliding or friction supports. For today, we will stick with one of the defaults, which is fully rigid. I click OK. All I need to do is to rotate my structure around here, select the bottom nodes, and my rigid supports are applied. Now, if I think that, okay, the supports are maybe a little bit too big for this structure, what's nice is that I can always right-click on these supports to decrease the size. So now you can see all of them are a little bit smaller in size. And the same thing goes for loads applied to our structure graphically as well, just something to point out there. Okay, so the geometry, the supports are completely done for our structure, so we want to move on to loading. For this, we want to create a new load case here, which is available in our tools. The first load case description will be dead load. The action category is set to dead. Action categories are important because the program needs to know what load factors to apply to which loads based on the ASCE 7 2016. The self-weight can automatically be accounted for within the dead load with this checkbox here. You can see -1 in the global Z direction. Our global coordinates are shown here. Creating a new load case, we'll call this one live. The action category will be set to live. Self-weight will be unchecked here. For our third load case, we'll call this one wind 1. The action category will be set to wind. And for our fourth and final case, we can even just make a copy of this and rename it to wind 2. So jumping to combination expressions, you can see here that the program is going to automatically create 2 expressions, LRFD and ASD. Now, if we're curious to know what exactly the expressions are in relation to the code, we can click on this little info button here. And this will show us all of the ASD load combinations directly from the ASCE 7 2016 section 2.4. So to lay this out a little bit more clear, we're going to jump to the load combinations. These are the actual load combinations generated by the program for both LRFD and ASD, only applicable to the load cases that we've defined. So here's where you'll see dead load, live load, wind 1, and wind 2. Lastly, we have our result combination. This is just an envelope solution. So if we're looking for maybe the highest or the max or min forces on our structure, for all of the LRFD load combinations, we'd want to look at a result combination. We also have a result combination for ASD set here for maybe seeing what the worst case deflections are for all load combinations together. So once this is done, we click OK, and we're back in RFEM. Now, utilizing this drop-down box, we want to make sure that we have the correct load case available here before we move on to applying loads to the member. Dead load, we're going to assume that just self-weight is fine for today's example. I'm not going to add on any other loads. So we'll scroll then to live load. Now for live load, under tools, generate loads, we have the option here from area loads on members via a plane. The first thing that we want to define is the load magnitude in the global Z direction. The magnitude here will be -0.05 kips per square foot. Then we just need to graphically select our corner nodes. So the first thing to select would be over on the left side of the structure. We're going to choose one plane here. Now I want to do the same thing on the right side of the structure, and what's nice is that I can do this all within one step. So now we have both planes defined on either structure or on either side of the structure. We can remove the influence from either single members by individually clicking them, or we can choose a reference member so that all members parallel to that reference member will be excluded from this load. So, for example, if I'd like to exclude these intermediate members between my top chords, all I need to do is just to select one of them. All of them are now not selected to be considered for the load. I click OK, and we can see here that the load is now shown graphically. Now, this is a pretty clean look, but if we're interested in how the load is being distributed to my members, I can right-click and display separately. So now we can see exactly what those member loads are based on their tributary area, and you'll notice that all of my intermediate HSS members were not taken into account. Moving on to wind load. So for wind load, under tools again, we have generate loads from either snow loads or wind loads. For wind loads, we have vertical walls with roof according to the ASCE 7 2016. Now, same thing goes for snow load as well. The wind and snow load generators are for pretty general type structures like what we're utilizing today and what you see in this picture. Anything outside of these general structures will need to be accounted for by manually applying those loads. So we want to put in here some velocity pressure and some other components that are important in terms of determining what the load should be according to the ASCE 7. We'll just go with the basic wind speed of 70 miles per hour. The building mean roof height, this can be set at 23.5 feet. The rest of the factors, we'll leave this as default. So typically this would all be blank, empty, but the program remembers my settings from another model that I currently have open. So what I can do is just redefine the base geometry here, and we want to pay careful attention that we select it with how the program suggests here. So for example, the base geometry, I'm just going to select my 4 nodes at the base, and once I close this circuit, it will jump back to the dialog box. And then for a dual pitch roof, I'm going to select my 6 nodes up here at the top of my roof. Now, if you incorrectly define this geometry in some way, the program will gray out the OK here, so you won't be able to apply the load, and you'll know that you did something wrong with selecting the geometry. We can generate case 1 and case 3 from the ASCE 7. We also can take into account minimum wind loads from this standard. Now, for the sake of today's example, I'm just going to account for minimum wind loads in 2 directions. For the first direction, we can set this to that load case that we previously created, LC3, which was wind 1. For the second wind load case, we can just set this to LC4. Now, again, you can remove influence from single members here or members parallel to a reference member. For our case, if I graphically select here my web members, maybe I don't want the wind load to be attributed to these web members with my truss. So I just graphically select all of them. You'll notice they're now not selected in red. I click OK. I click OK, and now the program is going to give me some more information based on the calculations that were done. I click OK, and now we can see these wind loads applied to the structure. This is for load case 3, and I can take a look at load case 4 from the other direction. Okay, so loading is complete. We can scroll through some of our load combinations to see how these are applied together. Now, not too many loads for today, but just know that loads can graphically be displayed here. So we're almost ready to run an analysis, but I do want to first jump back to the PowerPoint. So in the 2016 edition, the direct analysis method is talked about in Chapter C. And within Chapter C, we have several stability requirements. These would include member deformations, second order effects must be accounted for, such as P delta, P little delta, geometric imperfections, stiffness reduction, and uncertainty and stiffness and strength. for the sake of time today, we just don't have enough time to go through each one of these. But what I will say is that most of these didn't change. We'll go over what did change. But I previously did a webinar on AISC 360 2010 steel member design in RFEM with a recorded webinar available on our website and on our YouTube channel. But what I did is I really went into detail on Chapter C to show you exactly how to take into account each one of these stability requirements within RFEM. So a very helpful webinar if you're looking at P delta, stability requirements in general, and how to apply that to the structure. For today, though, what I do want to mention is just a change that was made in the 2016 to the adjustment of stiffness in section C2.3. Now, in the code, the AISC tells us that we must apply a 0.8 factor for axial and flexural stiffness. So it should be applied to all members that contribute to the lateral stability. Well, then it goes on further to say, well, I guess, avoid artificial distortions, let's go ahead and apply this to all members. Okay, no problem. 0.8 factor applied to those stiffnesses. There's also an additional tau sub B factor that should be applied to flexural stiffnesses. And tau sub B really depends on the required axial compressive strength. In other words, what is the axial force in the member due to the analysis, as well as the axial yield strength of our member? What is the capacity? And what's great about RFEM is that we're going to automatically determine for each iteration what tau sub B should be. So you might have several iterations for one load combination, and each time that tau sub B factor is going to update based on those requirements. Now, in the 2010 equations, you can see on the left here, we have required axial compressive strength. We also have the axial yield strength P sub Y. Now, comparing that to the 2016, realistically, the equation didn't change. What did change, though, is the P and S is no longer P sub Y. It's now called the cross-section compressive strength. And we have a small little section added in here for slender elements. Now, for non-slender elements, everything remains the same. For slender elements, though, we are no longer using the gross area, which is used for non-slender elements, but instead we're using the effective area. The effective area is defined in section E7, which is our chapter for compression. So that's something to keep in mind if you are designing with slender elements. Now, the code goes on further to say, hey, forget about all these equations, just apply the conservative factor, tau sub B equal to 1.0, if you want to apply some additional notional loads on top of that. And that's all explained in the standard, as well as I previously went over that in that last webinar. So how does that affect us for today? Well, going back to RFEM, what I'd like to do is to select the entire structure. I'm going to right click, and under member, I'm going to choose edit. The Modify Stiffness tab is currently set to none. That's default. But if we choose this drop-down box, you can see here, according to AISC 2010. So tau sub B can be set to iterative. Now, iterative is going to use those equations from the standard to determine what our tau sub B factor is for each iteration. We can also just simply set this equal to 1.0, as I mentioned, with some additional notional loads and such that you can apply to this structure. The flexural stiffness and axial stiffness multiplication factors, that 0.8 factor will be applied here. So the way that our program is set up, the gross area is something that's very easily known from RFEM, but the effective area is not determined until much later on within the steel module. So at this time, it's just a limitation of the program that we cannot account for slender members. Now, realistically, it's not too often that we're probably designing with slender members. It's definitely not unheard of. It's just not so common. So when you're not designing with slender members, nothing changes. You can continue to use the 2010 reference that we've selected here. If you are designing with slender members, use this option for all the other members. For your slender members, you have two options. You can either set this equal to 1 and apply those additional notional loads, or you can choose, let me change this back, or you can choose the multiplication factors here and to manually apply your reduction in stiffness to those slender members only. So that's just something to keep in mind. Now, today we don't have any slender members, so we can just keep everything as defined here. So now we are ready to finally run our calculation. So if I go to calculate all, what the program is going to do is it's going to cycle through my load cases, my load combinations. It is a nonlinear analysis. We are taking into account P delta effects and that tau beta stiffness reduction. And finally, we'll be presented with our analysis results within RFEM. So once this is done, as I mentioned before, the results tab is now available in our project navigator. The program immediately jumps to the deflections, so we can scroll through our load combinations to see how those deflections are changing based upon the different loads. We are also probably interested in the internal forces. So I can expand this tree here, select members, and maybe I want to take a look at my axial loads. Well, all of the axial loads are presented to us here graphically. Now, remember I said you have a lot of control over how you're viewing these results in the graphics window here. So under the display, for example, there's this whole results section. So under members, if maybe we want to change this to a color diagram, we can. So now we have a colored panel. We can change this to more of a wireframe view with the values written on here, or we can render the cross sections with colors as well. So again, very, I guess, flexible in how you view your results, and you do have a lot of power over that. For any individual member too, you can always right click and go to the results diagram. The results diagram is just going to give us a little bit more information for our various forces and deflections along the member length. We can even add, sum up these forces. We can average them out. You can add them to printout reports. You can change the load cases and combinations here. So this is just a more detailed look about what's going on for that particular member. Okay, so I think that concludes for the analysis portion. I did want to mention support reactions, of course, are all available here. So I do want to move on now to the design. So I want to make the clear distinction that we are now entering into one of the add-on modules. The add-on module RF-STEEL AISC can be accessed here in our project navigator. You can always right-click on any one of these modules, select it as your favorite to move it up to the top of the list. Under the add-on modules drop-down box, we can access them here. They're categorized a little bit better according to the various materials and applications, and we can choose RF-STEEL AISC. So up pops our add-on module. It's nothing more than a dialog box. I don't have to worry about remodeling anything, redefining cross-sections, materials, all those internal forces, everything is brought into this add-on module. All that we're doing is defining a little bit more information that's relevant to the AISC specifically in order to get that unity check from the standard. So what I want to first start off with is I'm going to rename this case. I go to File, Rename Case, and we'll call this one Columns. Now, by all means, you can design all members together in one case. If you like to keep them separate, such as columns, top chord, bottom chord, you can create different cases for them. So for this one, we'll start off with our columns. In the design, we have available here the 2016 edition, both LRFD and ASC. We also have the 2005 and 2010. So sticking with the LRFD 2016, I want to select graphically my column members. So back in RFEM, I highlight these column members. I click OK. The ultimate limit state design, I must define which load combinations I'd like to consider. So I'm going to move all of my LRFD load combinations on the right side of this tab here. As far as serviceability, I'm going to move all of my ASD load combinations because we can account for serviceability checks as well. Moving on down my list, my materials, steel A992 was automatically brought in. We don't need to do anything further here. Cross sections, same thing. W10 by 88 was brought in from RFEM, so we can continue to move on. Intermediate lateral restraints. This is going to affect our unbraced lengths for lateral torsional buckling and torsional buckling. You can see here that we can define lateral restraints for our top and bottom flanges. We can increase the number along the member length. And in turn, on this next tab, you can see that where that's going to affect those torsional buckling as well as weak axis unbraced lengths. But we'll get into that in just a minute. So if you do have some type of bracing for the top and bottom flange, you can apply that that here. Now, currently in development, and we hope to have this released soon at some point in the near future, is the ability to define top flange versus bottom flange versus both flanges versus no flanges braced for our intermediate bracing. Right now, you either need to consider all of them braced or none of them braced. So again, we hope that improvement will be available soon. Now, we don't have this consideration today for our columns. We'll assume that there's nothing bracing the top or bottom flange. Effective lengths is going to be our stability checks. We have our strong axis bending here, or buckling. We have our weak axis buckling, torsional buckling, and lateral torsional buckling. Now, because we are designing these members per the direct analysis method in Chapter C, the code tells us that we can set the effective length factors equal to 1.0. This is in contrast to the effective length method in Appendix 7, where you do need to adjust those K factors. So moving on with Chapter C, then, we can leave these all as default as 1. Now, the unbraced length is going to default to the full member length. Unbraced lengths are incredibly important because they really do affect our design. So the software is only as smart as what you model. So it's going to default to the full member length. Now, if we had some additional members in here that we would consider braced in either the strong or weak axis, we would want to adjust the unbraced length. And we'll actually do that with our next case later today. For both strong and weak axis, I'm going to assume that it is the full length, the full 20 feet for my unbraced length for both buckling, torsional buckling, lateral torsional buckling. So we can move on. The design parameters are going to be some additional variables. For example, our C sub B factor, which we can see that's default set to 1.0, which is a little bit more conservative. We can change this to equation F1-1. Or you can manually override this. We also have some additional variables here. These are just important for some of the various equations in the AISC. Serviceability data. So this is how we check our deflections. The first thing I want to do is to choose member from my drop-down box here, and then graphically I can just go back into RFEM and select my columns. So I select these columns, I click OK, and now each one of those members is listed here. The reference length is again going to be the full length of the member, the 20 feet. We can add in here a pre-camber if we had one for deflection considerations. And then the beam type either needs to be set to beam or a cantilever. So the question is, well, okay, we've identified how we're going to compare these deflections, but what exactly is it going to be compared to? What is my limiting deflection ratio? Well, under the Details tab, we have our serviceability input here. So you can see that the limiting deflection is set at L/360 for simply supported, L/180 for cantilevers. Now, by all means, you can override this information as you see fit for your limiting deflection ratios. The deformation is either relative to the shifted member ends or the undeformed system. With the shifted member ends, the deflection will only be measured from the new distorted shape of that member and its member ends. That is in comparison to the undeformed system, where the deflection will be measured from the original structure location before we've applied any loads to it. So that can give you very different results, and it's up to you as an engineer which deformation you would like to measure. We'll keep this first case as the shifted member ends. I click OK, and I'm ready to run a calculation. Now, you see that solves within a split second, and that's because we already have our internal forces from RFEM. All that we're doing is applying these equations from the AISC to give us our unity check. And now our results tables are available to us. We can view design by load case. We can view design by cross-section. We only have one cross-section available here. We can view design by member. Now, keep in mind you can export all of this information directly to Microsoft Excel if you want to sort a bit further. And as I'm taking a look at design by member and I'm scrolling down through this table, you'll notice that everything is synced up to RFEM in the background. So with an extremely large structure, you can imagine that this is really beneficial to understand where exactly you're at. Now, even more so, you'll see this big red arrow. That red arrow is pointing you to the location of the controlling internal force for that particular check. So if we're looking at member number 79 here, you can see that we have all of the code checks for each chapter listed here, chapter F, chapter G, chapter E, and H. For each one of these, if we go to lateral torsional buckling, for example, you can see the cross-section type listed here and how it's classified, whether that's non-slender, slender, compact, non-compact. We have all of the variables that go into play for determining what that lateral torsional buckling unity check is, along with the code references. So very, very clear in understanding where the program came up with its numbers. It's definitely not a black box. Now, this is great, but you might say, well, gosh, that's just really too much information. You know, I'm only interested in the controlling single code check for each member. Well, that's fine. You can easily filter here according to the max. Now, once I hit this filter button, it's only going to give me my controlling equations, which you can see serviceability, for example, controls with a lot of these, chapter H for member number 109. So that way you're not filtering through all of the code checks. We also have the material takeoff available here. Now, going to the graphics view, this is going to display our results. We're still technically in the add-on module RF-STEEL AISC, but we're viewing everything back in RFEM. So with this drop-down box, you can see here RF-STEEL AISC is selected, and we can take a look at our ultimate limit state design. So just taking a look at those code checks. We can also take a look at serviceability, which it looks like most are 0.25, for example, and controlling at the midspan. So jumping back to RF-STEEL AISC, that really shows you the results for just our columns designing our members. Real quickly, I just want to mention optimization. Back under the cross sections, you can see here that the W10/88 has our max design ratio listed here after we solve for it, 0.28. Now, we can optimize. The default is set to no, but we choose this drop-down box and we have a couple options here. You can optimize from the current row, meaning the program is going to choose any W shape from the AISC section. The other option is to choose one of your favorites list. So remember way back when we first drew this column, I had my favorites list USA with about, I don't know, 7 10-by shapes. So with this favorites USA now, if I want to optimize from just those 10 or so shapes, those W10-bys, then I can choose this option. I can hit calculate. Now what the program is going to do is it's going to kind of give you an estimation based on the old internal forces with the old cross section and say, well, I think approximately you should get about 0.54. So, you know, that's a little bit better than 0.23 or whatever we were seeing before. But you'll notice here that this is highlighted in blue, and this is telling you the cross section in RFEM is different from the cross section in this module. So what you need to do is to right click and export this cross section back out to RFEM, rerun your analysis so that we get the true internal forces based on the correct stiffness with our new shape. What it's showing now is just an approximation. That's why it's highlighted in blue. In turn, I can right click and import the cross section from RFEM to bring back in that W10/88. So that's what I want to show you for this first case and design of columns. Next, I'd like to create a second case. So we'll go to File, New Case, and this one we will call Bottom Chord. I click OK. It's asking me to save changes to my original case. That's fine. So now you can see I can easily toggle back and forth between either case. So that's why sometimes it's nice to keep them in separate cases if you want to design sets of members separately. So for this next case, what I'd like to go into a little bit more detail is the design of members versus sets of members. Now, ultimately, we're going to end up with the same results for members versus sets of members. It's just a different approach, and I think that there are some advantages to sets of members over members. So what we'd like to first define here, LRFD 2016, that's fine. And I'm going to select here, rotate my model. I'm going to zoom in and select my individual members for my bottom chord at this second frame. Oops, not that member. And I click OK. In turn, I'm going to select a set of members. So a set of members was automatically created by the program when I generated these truss members. You can see here there's a faint dotted line around all of my bottom members for this bottom chord. That's called a set of members. I select it, I click OK. Let me quickly jump back to RFEM to explain what a set of members is further. So the program automatically created those sets of members, that was done for both the bottom chord and the top chord. So if I zoom in here, here's this faint dotted line around the bottom chord. Now the top chord, if I highlight this faint dotted line and select it, is the entire top chord. So this can actually be designed as one continuous member. Now, what's very powerful about sets of members is it doesn't necessarily have to be in a straight line. So it does need to be in a single plane though, but it can have several bends to it. A great example, of course, is this top chord, but we could even design this column, this top chord, and this other column as one continuous member if we wanted to with a set of members. Now, the program automatically did that for us. Just to let you know, you can hold down your control key, select several members, right-click, choose the option Create Set of Members, and that's how we can generate a continuous member here with that dotted line around all of them. So we're not doing that with these members, but jumping back to my current module here, which is the RF-STEEL AISC, and my bottom chord, that's kind of the difference in selecting members versus sets of members. So again, I want to choose my LRFD load combinations for ultimate limit state design. Serviceability, we will choose our ASD load combinations. Moving on down the list to materials. So we had chosen Steel A1085 for HSS members. Now, this is now recognized in the 2016 spec as an approved HSS material, as I mentioned before. Now, with 1085 and 1065, these have more stringent wall tolerances than the previous A500. So what this means is that the code tells us we can now use the full nominal wall thickness for design. This is in comparison to the A500 where we had to use 93% of the thickness. So how do we account for the full nominal thickness with this new material? Under the Details tab, you'll see here a section, Design Wall Thickness of HSS. Here is where we can uncheck this option so that we don't reduce the nominal thickness for HSS according to B4.2. So when using the 1085 or 1065, we can account for the full thickness. Cross sections, HSS 12x8 brought in from RFEM. Intermediate lateral restraints, same concept as before for both our members and sets of members. Now we don't have any top or bottom restraints here for HSS members. It's just not relevant. So we will continue to move on. So effective lengths for members, we also have effective lengths for sets of members. So we have two separate tables here. So looking at our members, you'll see that the buckling length for strong axis, weak axis, and both our torsional buckling and lateral torsional buckling are set to 8.33. This is incorrect. Again, the program only knows how the information is input into the model. So this is why it's incredibly important to pay attention to unbraced lengths. I would argue that for this bottom chord, the unbraced length for the strong axis is the full 50 feet. I don't have any columns bracing the member below it, so I'd like to account for that full length. Well, what I can do is to graphically measure the full 50 feet here from end node to end node. The program will calculate that up as 50 feet. I can scroll down to my next cell and hit the F8 key to copy that input for every single member. Now, for my weak axis direction, I would say that this is most likely 25 feet. Remember that we left in this intermediate HSS member bracing it in the weak axis direction at the midpoint. So again, we can use our measure tool here from one end node to the center. That populates as 25 feet. Using my F8 key, then I can enter in that information for all of those members. Now, as for torsional buckling and lateral torsional buckling, again, this depends on your connection types. So it's really up to the engineer's discretion. I might say in this type of scenario that this small HSS member is bracing it for both torsional buckling and lateral torsional buckling as well. So what I can do, just like what we do in Microsoft Excel, highlight all these cells, hit the Control C, and I can Control V and paste them into the adjacent cells. Same goes for lateral torsional buckling. So now that we have set all the unbraced lengths for our members here, we want to move on and do the same thing for sets of members. Now we have one single set of members listed, and the program defaults to the full 50 feet in length. Now we can manually override this, but what I'd like to do is to jump down to the nodal supports here. This was not available previously with just members. It's only available with sets of members. And this is where a big difference comes in for members versus sets of members. With a set of members, because we don't require it to be in a continuous straight line, the program will actually run an internal eigenvalue analysis for this single set of members. This will in turn come up with the buckling modes for that particular set of members and a critical buckling moment. So instead of for weak axis buckling, strong axis torsional buckling, lateral torsional buckling, we're going to forego all that for sets of members according to the AISC, and instead we're going to run an eigenvalue analysis, which is a much more theoretical approach to come up with a critical buckling moment to take the place of that. So it's just more accurate. So for this, with our nodal supports, you can see here our set of members is highlighted. I can zoom in here and change this to my local coordinate system. So for my eigenvalue analysis, the program has to support these members internally for this quick little, I guess, on the side analysis to determine what our critical buckling moment is. It automatically places these supports at either end. Each node along the set of members length has 4 degrees of freedom. The lateral translation, you can see here, we also have some rotational restraint, and we can even take into account warping. For example, if you have warping, we can check this checkbox, go into the details here, and account for warp stiffening such as an end plate. Maybe you have a channel section or an angle. We just specify the material here, we specify the geometry of the warp stiffening, and the program will calculate a resulting warping spring. So I click OK out of this, and what will happen is we'll get a warping spring here that will automatically be accounted for within the eigenvalue analysis to give us a higher critical buckling moment. So pretty powerful that for sets of members versus what we don't have for members. Now, for this particular set of members, remember we have an intermediate HSS framing into it. So what I can do is just to graphically select that node back in RFEM. I do want to brace it laterally, and I want to apply a rotational restraint. Now, each one of these has its own local axes as well, X prime, Z prime, Y prime, which are mentioned here. Member hinges, same type of concept. If you had any member hinges along the member length, such as shear releases, moment releases, warping releases, you can account for them here, which will affect our eigenvalue analysis. So jumping back up to the effective lengths for sets of members, you can see now the buckling about the weak axis was automatically updated to 25 feet. Torsional buckling, 25 feet. Lateral torsional buckling will be automatically calculated based on the eigenvalue analysis. Design parameters, nothing new here. These are just these various variables that go into play for our equations. Lastly, serviceability data. So the question here is we want to compare serviceability for both our members and sets of members. The first thing we want to do here is choose member, and then we can graphically select those bottom chord members just as we previously had done to check the serviceability. I click OK. Now the reference length is set to 8.33. We actually want to override this here and set this to the full 50 feet. Now again, I can just simply measure back in RFEM at the click of 2 buttons. I hit my F8 key, and now that will set the reference length to the full 50 feet for each one of these members. For my set of members, I'm going to choose that from my drop-down box and graphically choose my set of members. I click OK. This is set to 50 feet by default, so that's great. So now we're kind of comparing the same thing here. We should come up with the same serviceability check. But the one thing we do need to do under the details button is change this option here, the deformation relative. We cannot use the shifted member ends. That's just not comparing apples to apples. We have to use the undeformed system. Otherwise, we're going to get extremely different results. So in order to compare sets of members versus members, we have to compare that to the undeformed system, and I click OK. So now I'm ready to run my calculation. Again, it solves within a quick second, and you'll notice here that I have my results, again, available according to the load case, according to the cross-section, which we only designed for one cross-section, but we also have design by sets of members and design by member. So two separate tables there. If we're looking at design by member, we already went over most of this, but I did want to show you, if we take a look at one of these HSS members, is this section here, lateral torsional buckling. For this is a brand new section to the 2016 edition for HSS members. So let's jump back to the PowerPoint to discuss that a little bit further. So this is under the section HSS, lateral torsional buckling, section F7.4. So LTB considerations were added here, which is new to the 2016 standard. They are dependent on unbraced lengths. So this includes the manual unbraced lengths that we entered in, our L sub B, and then L sub P and L sub R are our limiting bracing lengths, which are calculated according to our cross section. Now, depending on where you fall within that range, that's where your nominal flexural strength is going to be calculated, and it could vary depending on where you fall. So what's really great about RFEM is that not only have we added this section here per the 2016, but we also give you all of this information such as LB, LP, and LR. So you can find out exactly where you fall within this range. Then we'll be given our nominal flexural strength, M sub N here, according to F7-10, which correlates back to the standard F7-10. The code does have a user's note saying essentially lateral torsional buckling probably won't control in most cases for HSS. Realistically, deflection will usually control, and that's definitely the case with our model today. Lateral torsional buckling is really low, and serviceability is much higher code check. So just something that's interesting there. So going back to the model, we can see here again that lateral torsional buckling. Now, if I go to my sets of members, and we only design for one set of members, I don't see lateral torsional buckling here. And that's simply because, like I said, we forego those analytical equations from the AISC, and instead, under stability analysis, we run our eigenvalue analysis to come up with the elastic critical moment for lateral torsional buckling. You can see the amplifier that was determined here from that, and we come up with 6,400 kip feet, which is incredibly high, but that's what our stability checks are going to be compared to. Now, in reality, what ends up controlling in this case would be yielding from our strong axis, which is 255 kips per feet. But that is a huge difference between sets of members versus members. So something to keep into consideration there. Again, all the code references are listed here. Okay, so we can take a look here at the various code checks in our table. I think we see members versus sets of members. We do get the same code check. What we can also do, though, is view the information graphically. I think this is a little bit easier to compare to make sure that we are getting the same results. So what I'm going to do is I'm going to highlight those bottom chords by holding down my control key. Maybe I create up here in my tools a visibility by selected objects, so now we can clearly lay this out. Well, this looks like our serviceability limit state design according to our ADA module, and the results are identical, which is exactly what we would expect. Same thing goes for the ultimate limit state. We can see here we have these same numbers along the length for both bottom chords. So again, different approaches, but you should come up with the same results. Again, but you have to pay very careful attention to things like unbraced lengths. Okay, so that really concludes our structure today, but there are several more points that I wanted to go over according to the 2016 updates that we just simply don't have these members available in our structure today. So this is definitely not an exhaustive list, but I just wanted to point out some of the changes that you'll see within the ADA module RF-STEEL AISC in reference to the 2016 edition. For example, members with slender elements in section E7. This was completely revamped to line up more along the lines with the AISI standard, which is for cold form steel. For example, the nominal compressive strength, P sub n, which comes from equation E7-1, we can see over here on the left side for the 2010 version, it's just our critical stress times our gross area. Well, now for the 2016 version, it is the critical stress times the effective area. So this just sounds almost identical to what we saw in chapter C. So our critical stress remains unchanged, but A sub B is completely different. It depends on some lambda values here, which is our width to thickness ratios of our elements, our local elements. C sub 1 and C sub 2, which are new for effective width imperfection adjustment factors according to table E7.1 and some other variables. So you can see my small little example here that I did in RFEM, and then we can take a look at the results within the RF-STEEL AISC. Now, again, what's really powerful is that this is a equal leg angle, but for each, each section type, each leg, we're going to give you the classification, and you're going to see that's slender. We even have the lambda values listed here, so you can know exactly how those were determined from this particular cross section. Then the effective area is listed here, A sub E. We have our critical stress, and it's just simply a multiplication of those to come up with our nominal compressive strength according to equation E7-1, which is listed here, and again correlates back to the standard. HSS web local buckling in section F7.3. Well, here the consideration was added for slender web sections. So this is in F7.3C. You can see my example of my HSS member, which is completely exaggerated so that we have a slender web. The code does note that no HSS sections, which are recognized within the AISC, have slender webs. So this would pretty much have to be a custom section in order to finally see this check within the add-on module. But nevertheless, it is available here. If you do have a slender web, you can see the program gives you that information that it's classified as slender, and then we'll see some things here like reduction factor, the buckling stress, and ultimately the nominal flexural stress from section F7. T's and double angles, this was another major revision in section F9. Here, the lateral torsional buckling was revised in section F9.2, and in particular for stems and legs and tension. Here, the code has added unbraced length consideration. So this is similar to our HSS sections. Depending on where you're falling within this range with your unbraced length, well, then that's going to adjust that equation being used. Again, for my example here, you can see just a simple T section, and chapter F is listed here with lateral torsional buckling. We're going to lay out for you the brace lengths and the limiting length LB, LP, and LR, so you can see where you land within that scenario. And then the nominal flexural strength will be given here. Now also the T-stem local buckling according to section F9.4a, there were some revised equations here. So if you're running the 2010 versus 2016 in the module, you're going to see slightly different results available there. Okay, so lastly, chapter 8 for our interaction equations. It is noted here that all throughout this chapter, there is the reference to required strengths. You can see in my example here, required axial strength, required flexural strength. Well, after all of these required strengths is the small note here determined in accordance with chapter C. You'll remember that chapter C is our direct analysis method. I think that this is a pretty big milestone. Previously, the direct analysis method was never really differentiated much from the effective length method, but now in the 2016 version, this really seems like this is the way that the AISC is pushing engineers to determine what our internal forces are. So again, I think that that's why that previous webinar that I did, according to the 2010 version, because realistically nothing changed within that chapter except for the small section for stiffness reduction, will be extremely useful, as this seems to be the way that the AISC is headed towards. Okay, so that concludes the webinar for today. I know that was an incredible amount of information at one time. We have our website, dlubal.com, which gives much more information about RFEM, our add-on modules, and many other technical articles and things like that. You can also follow us online on our social media sites. You heard me mention our YouTube channel that has all of our previously recorded webinars that you can watch on the different topics like timber, steel, aluminum, glass, cross-laminated timber. Our email here in our Philadelphia office is info-us@dlubal.com. Our phone number is 267-702-2815 if you have any questions about today's webinar or anything else. We will have many more upcoming webinars this year. You can register on our website at dlubal.com under support and learning webinars. As most of you know today, though, I send out a couple reminder emails, maybe about a week in advance, that you can always sign up through as well. Now, many of you are wanting PDH credit for today. That's great. I'll be happy to issue that certificate. If you can please send me an email to info-us@dlubal.com. Let me know who is in attendance today, and the other thing that I ask is that you were in attendance for the full 60 minutes in order to get the 1 PDH credit that the states require. Again, that email is info-us@dlubal, DLUBAL.com. With that said, I want to thank everyone for attending today, and as always, I hope to see you at the next webinar. Thank you.